Everybody, Samuel Singer here, the founder and executive director of Wyoming Stargazing. Thanks for joining me, and welcome to Mind Bending Astronomy. In every episode, we'll share with you, a mind-bending fact about astronomy. Last time we talked about the space-time interval and how it's the only mathematical formula that provides universally agreed upon results of the time an event took place between two objects, where it took place, and what object could have influenced the other object. In other words, it allows us to calculate the causal links between objects in the universe. We also reviewed the connections that we made between light, electromagnetic radiation, photons, quantum mechanics, locality, and the insights of several 19th and 20th century physicists, including Einstein. Einstein's insights into the nature of reality extend way beyond the super small world of quantum mechanics. In fact, he also created the current best theories we have that explain the largest size scales of the universe. Before we delve into those theories, we need to take a look at what mass really is and what Einstein meant by mass in his famous equation E equals mc squared. Most of us think about mass as the amount of stuff or material in an object, and that works pretty well with everyday applications. However, Einstein's equations tell us that energy, E, is really just mass, m, multiplied by the speed of light, or causality, c squared. Said in another way, mass is just a measure of how much energy there is inside something. Well, there are lots of different types of energy, such as potential energy, thermal energy, and kinetic energy. Does that mean that all those forms of energy add up to the total mass of an object? Yep, they do. Am I really suggesting that a moving object has more mass than an object at rest? Yes, that's what I'm saying. It's only a tiny bit more mass, because the total amount of mass added is the energy divided by the speed of light squared, which is a huge number, but that tiny bit of added mass is actually there. Okay, so maybe you're thinking, well, what about gravity? Is gravity affected by this contribution of mass from energy? Well, it turns out that an object being accelerated because of gravity feels exactly the same force on it as an object accelerated out in empty space, accelerated up to the same speed. The force needed to accelerate that object is the force needed to overcome an object's resistance to motion, or acceleration. And that's what mass is, the resistance to motion, or the resistance to acceleration. Gravitational mass, that mass felt when applying a force on something, is indistinguishable from the other type of mass that I was just talking about, getting something to move, which is called inertial mass. But wait, there's more. The other truly bizarre attribute of mass is that it emerges from massless particles, like photons, when they're confined within some volume, such as a box. The pressure the photons moving around inside the box exert a pressure on the walls that behaves exactly the same way as if there was some object with mass inside the box, if it's all in a gravitational field. Mass emerges in a similar way for subatomic particles like protons and neutrons, not from the mass of their elementary particles they're made from, called quarks, but rather from the potential energy of those quarks confined within them. So we end up with mass not being the amount of stuff in an object, but rather being an emergent property that is either the resistance to motion of that object itself or the resistance to motion of its constituent parts within it. Crazy stuff, but it's what mass is. To hear more about this, check out the videos that I have in the transcript of this talk by Dr. Matt O'Dowd and Gabe on Spacetime. Both excellent videos. Next time, we're going to continue to explore Einstein's insights into the nature of space, time, and gravity. Until then, be well, and don't forget to look up.